to do a whole load of 3G testing, and Bryant delivered to our workshop hundreds of meters of all the different kind of manufacturer cables that were 3G ready, and using Tektronix 8000 series, we tested them, to destruction. So from the, I think we started at 200 meters, and essentially, I had a wiring guy chop, re-end, and we got all the way down to, very short lengths for all those different cable types, and recorded all that. And that's one of the PDFs that's in that URL I've dropped into the chat. I think it's called Tech Plots, and you can see exactly how the eye diagram on an 8000 series varies between those 6 different cable types and distance. And so we'll go over all that a bit later, and what we discovered makes the real difference and what makes very little difference. And the clue is gold-plated connectors make no difference whatsoever. So we'll kick off this morning with a presentation that I've given a few times, which is principally for people who are looking to move to 12G. So as you'll know, that for 4K video, or UHD as we should call it in television, I'll use the terms interchangeably, I'm aware they're not quite the same, that for UHD, there's a couple of standards where you use quad link 3G, so 4 pieces of 3G coax, and the pixels are arranged in slightly different ways depending on which standard you've gone with, or you can send the whole UHD raster down a single SDi cable called 12 gigabit link, which SMPTE 2088, or I can't remember what the standard number is, but that really gets you into a lot of excitement, and I will show you all the same style of testing we did for 12G cable, and just what a frustration that is, because even though 3G is starting to bite you guys in the backside, I don't doubt that in 2 years' time 12G will be biting you guys in the backside. And as with all these things, it's just a distance bandwidth product. So as you double the data rate, you half the effective distance that you can send that signal down the same piece of cable. And so 12 gigabit per second video is a doubling, 3G to 6G to 12G. So it's 2 doublings. So it's 2 octaves, as we'd say in frequency terms. It's 2 octaves higher frequency. And so as a consequence, all the same principles apply. This is just flipping physics after all. But it's it's 4 times as bad as it is with 3G. And so, of course, the answer is fiber. But as I said, we'll get into that a little bit later. So Michael's sort of main 4 sort of bullet points were an appreciation of the 3G signal and how it's different from a 1.5 gig signal. So we've lived with 1.5 gig HD SDi for a couple of decades now. I think the first job I worked on where everything was 1.5 gig HD SDi was Band of Brothers back in the late 90s. But that was ubiquitous for a long time, and it was HD cam VTRs, and it was how telly to this day is all done. 422, 50i, 50 interlaced fields. It's how we do telly and have done for a long time. But 3G doubles that data rate, allows you to have 50p, 50 progressive frames rather than 50 interlaced frames. It allows you to do clever things with RGB if you're working in sort of digital film space. If you want 2K RGB at lower frame rates, 24p or 2398p, and all that kind of stuff. But 3G brings all its own problems. That sort of Michael's second bullet point was how to measure 3G signals. And what to look for to find out when things are near the hairy edge, when things are starting to get ready to fall apart. And you can see now on screen my waveform monitor, which is a Leader LV5490 with the physical layer option. And you can see I'm feeding it a test signal, which is it's a bit higher res than HD. It's 2K at 50p. So packing the 3G signal. And so that's what we'll use as our measurement examples. Now, I don't know if you guys, I'm sure I've seen Leader at Doc 10 when I've been in your grading rooms, and I'm sure I've seen Tektronix when I've been in your MCR. The principles are exactly the same, and a lot of my screen grabs are from Tektronix, and a lot of my screen grabs, and in fact, today's live sort of instrument examples will be from a Leader LV5490, but the principles are all exactly the same. An eye pattern is an eye pattern. All the measurements are exactly the same. 120 picoseconds of rise time and all those kind of things are defined in the EBU documents, which we'll go over, but they're all the same. But it just so happens I have a leader. I don't have a Tektronix here with me, so we'll be using the leader today. But you know, it's just a question of different button pushes and different styles. There was also a question about limitation of sending 3G over distance. You know, what are those considerations? And as I say, I've done all that with multiple different cable types, and so I can show you exactly what those results look like. And you'll always find people who can say, yes, I know your test results suggest that 60 meters is the limit for the best quality cable with the best quality sending equipment and the lowest return loss receiving equipment. But I've seen 3G going over 100 meters, and absolutely. But if you want to stay inside what the SMPTE specification says, so SMPTE 2082, if you want to stay within a decent quality eye pattern, and you don't want to sail too close to the wind, you don't want to be in a position where, you know, when it gets a bit warmer, or you know, when another bundle of cables gets laid on top of the cables that signal's going down, you don't want to be near the hairy edge. You know, you don't want to be in a position where you are millivolts away from seeing sparkly pixels. You want to be well inside the margin of error. So we'll talk a lot about that as well. And best practices for 3G cabling. You know, some of the things you need to dissuade your wireman from doing, and that kind of thing. And as I say, gold BNCs are not the answer, even though a lot of people will sell you them. So I'm going to share an image. Should be able to see it now, yeah? So this is something I saw at the the station in Cornwall, where the first submarine cables that go to America start from. And this is a sample of the coax cable they used in Victorian times to carry a single telegraph signal. So, you know, forget 3 gigabits per second, forget flipping 270 megabits per second standard definition SDi. This carries a Morse code ... type signal, very remarkably low bandwidth. And you can't tell from the picture, but this thing's as thick as your arm. It really is, and you know, very well armored. And this is meant to sit at the bottom of the ocean and carry that signal. And this was the very first cable they laid in the 1880s to provide telegraph communication between you know, England and New York. And it failed after only a few months because of water intrusion. You know, basically the pressure at those depths, the damp was just able to push its way into the cable. And that you can see the white dielectric material that surrounds the central conducting core. That's made of wax, the same stuff they made candles out of. And it didn't take very long for that very high pressure moisture to force its way into the wax, completely changing the characteristics of the cable. So the cable was no longer a good conductor. And as they realized this was happening, they just turned up the volts. They basically just turned up the power they were sending down the cable to try and defeat the fact the cable got very noisy because of the water intrusion. And before you knew it, the cable just burnt out somewhere under the ocean. And so those many millions of Victorian pounds invested were wasted. So that's just a little something to think about. If you think you've got problems with your cabling around your facility, pity the poor Victorian electrical engineer who had to deal with that. Anyway, so where are my notes? So here are bullet points. A history of digital video transport on SDi. You know, it's always useful to know where we come from, to know where we're going. Some of the variations and adaptions that SDi is used for. SDi is not just used for synchronous video from cameras to monitors and that kind of thing. Physical layer considerations, making measurements, which really I suppose is the meat of what you guys are after. And what cable does to the signal, you know, meter upon meter of cable, you know, the damage it does to those bits as they're being pushed down the signal. And you often hear people talking about the eye pattern closing, and that's why we call it an eye pattern, because as the eye pattern closes, you know, we know we're getting closer and closer to the hairy edge of where it won't work anymore. What are our options? Fiber optic obviously allows cable to go, the SDi signal to go much further. You know, 80-kilometer SDi SFPs are now reasonable money. They're not the silly money they were a couple of years ago. And so sending SDi without having to encode it into IP or that kind of stuff is now very doable over very long distances with fiber. It's why, you know, SMPTE camera optical triax is the way it is and such. And then we'll talk a bit about 12G. Does it even work? And it's bedeviled with problems. So history of SDi. SDi, and please, stop me. I'll just rabbit on until I get to the end of this. If I've skipped over something you want me to go back over, just stop me and we can hover around something. Or if I'm majoring on something that is meat and veg to you guys and you're very comfortable with it already, then again push me on, kind of thing. Because there's nothing worse than an hour later taking a breath and realizing that nobody really was paying any attention. SDi dates from the 80s. Digital video, none of you are probably old enough, but digital video was originally a big D25 connector with twisted pair cable, and it would go a few meters, and that was it. And so everything had to be within the same couple of bays in the machine room. But SMPTE proposed a serial digital interface in the late 80s. However, the thing that nobody really remembers is that it wasn't the SMPTE standard that won out. There were a few products from people like Thomson and others that used the SMPTE standards, but it was actually Sony's version that won out, and kind of Sony gifted it to the industry in the early 90s. With the sort of second generation of D1 VTRs, and before Digibeta was launched, Sony gifted us the SDi that we know and love today. And SMPTE very quickly kind of rewrote all their standards to encompass the Sony standard, because that was the winner, kind of thing. We're up to a point now where SMPTE 2083 specifies a data rate up to 24 gigabits per second, which is those very high frame rates, 4K raster with RGB, 12 bits, all those kind of much higher specs than we really need in television, but appeals to the film people and all that kind of stuff. All of what we're talking about now dates back to Sony and the early 90s. So again, there's a product that you may be all far too young to remember, but it was Arger's first product, the CP10, and that was a little adapter that Arger brought out, and in fact several other people did as well. That was just used the Sony, I can't remember the chip model number, but it was ubiquitous at the time, to go between the parallel port output on the back of a D1 machine and BNCs. And used to see those all over the place. Every flipping machine room had hundreds of these hanging off equipment and kind of sitting on the shelf ready to go. This is kind of parallel digital video in and serial digital video out. But there was another one that went the other way, much as we get fiber to BNC adapters nowadays. So here's a little bit of history. It's the list of SMPTE standards that relate to SDi, and there's 259, which is it's Digibeta, and it had several variations which you may not be aware of. So 360 megabits per second was the standard that SMPTE hoped we'd all adopt for widescreen for 16:9. SDi, because if you think about it, if you record a 4:3 picture onto a Digibeta or a 16:9, you fill up the same number of pixels, but when you expand that raster to fill a 16:9 monitor, you lose some resolution. So widescreen standard definition, you could argue it's a slightly lower resolution than 4:3 standard definition. And so 360 megabits was never really adopted. There are a few things that could support it. There was some models of Telecine that would do it and stuff. And then you got these two, 143 megabits and 177 megabits. They were for composite digital. So if you remember D2 VTRs and D3 VTRs, they were the data rates they could use. And again, one was intended for 4:3 and one was intended for 16:9, but somewhat forgotten. Then there was even a standard for 50p and 60p at standard definition, and that was the 540 megabit, the 344 SMPTE, which again, we never really took off. We never really dealt with it, but it was a thing. And then we get into the standards that we all know, love, and remember well. The 292, which is that's HD cam essentially. That's HD SDi going down a single piece of coax cable carrying 422, maximum of 60i. And then we've got a couple of 3G standards. We've got dual link, which if you did any work in digital film was a thing in the noughties. and then 3G, which is kind of where we find ourselves today. And then we've got some higher res versions that kind of are suitable for 4K and UHD, 2160 line working. It's interesting that 6G was a Blackmagic standard, which SMPTE had to sort of rush to ratify. So if you look at these sort of standards here, these sort of specifications, you'll notice that they're very similar, physically to what we would have had for composite video or for analog component. And that was very much the intention, that we'd use the same style of cable to send digital video down. 75 ohm nominal impedance coax with BNC connectors and Musa patch panels and all those things. The signal amplitude of 800 millivolts is remarkably close to this, what we had for analog video, and uncompressed digital component signals. So typically YCBCR, YUV if you're a very lazy engineer. I know U and V aren't the same as CB and CR, but we use them interchangeably. And the data's encoded in NRZI, non-return to zero interface format. And what does that mean? Well, if you imagine you had a whole screen of just black video, all those pixels are 0, 0 for both the luminance channel and for the two color difference channels. And so you've got to send at 1.5 gigabits per second down a cable, lots of zeros. That very quickly just becomes untenable, because not only is it very hard to recover the clock from the other end, but you've now put a DC offset on the signal. And so any equipment that's going through that clamps the signal, you run into trouble. And so we have to scramble the data in a sense. We have to apply an encoding to it so that we're not just sending lots of zeros or lots of ones. We have to have constant clock edges in the data to keep that correct. It's also self-synchronizing and self-clocking. So SDi carries a clock within it, so you don't have to send a separate word clock, like is often useful for AES audio. And there are special sequences of ones and zeros that signify certain things: the start of an SDi frame, the end of an SDi frame, and lots of other things within the data that you can dig down and sort of discover, so that manufacturers don't have to render out a full frame of SDi to figure out where the first line is and where the last line is. It's that there are unique bit pans within the signal that tell the equipment, here's where it's starting, or here where this is happening, or this is metadata. Don't try and turn this into pixels, kind of thing. And so SDi, was proved to be a remarkably robust interface, remarkably usable, and so just got extended, ad nauseum. Dual link, as I say, was used a lot in digital film, where people wanted to be able to send RGB rather than YCBCR, and more than that, RGB, but maybe with an alpha channel as well, so maybe with a key channel as well. So you'd need that 444 signal structure, rather than what you get with just normal 1.5 gigabit SDi, which is a 422. So the two color components are at half the sample rate of the luminance. And so that was typically done over 2 wires. And so the first wire would carry the red and subsampled versions of green and blue, and the second wire would carry the other half of the green and the blue and the alpha channel. And if you look on the back of a Sony 5500 VTR, an HD Cam SR, you'll see dual link. ASI, which, if you've ever worked in transmission departments, is the way we move encoded, MPEG transport streams around the place. So we've gone from carrying synchronous digital video, where frames start and stop at certain points, where we've got signals that have to be synchronous, and this is the start of a video frame, this is the end of a video frame, this is where pixels are coming, etc. To ASI, asynchronous transmission mode, asynchronous signal interface, where we're carrying things that are now of a variable data rate. The MPEG transport stream, the data rate varies depending on the complexity of the pictures and how many transport streams we've multiplexed onto a cable. So that's an interesting turn of events. But if you're a big transmission facility, it's very useful to be able to route ASI through the same router that you're sending SDi, and sending it through the same patch panels and down the same cables as SDi is. And then there's a couple of other interesting ones. SDTI, you might have seen that on the back of a VTR, where you can send the off-tape data, the off-tape compressed data, down an SDi cable and do it at double real time. So you could dub between two HDCAM machines at double real time by exploiting the fact that the SDTI spigot, the little BNC on the back, could carry full data rate, even though it was only having to carry compressed data. So all these kind of interesting variations. And then we've got sort of various optical standards, and the one we just see everywhere, you buy those cheap and cheerful little Blackmagic converters, is SMPTE 297 from 2006, and that's basically just a way of taking the copper cable, the BNC with the voltages on it, and turning those into exactly the same numbers, but pushing them down a fiber optic cable. And so that's how we do SDi over distance, whether it's down a single fiber, from the gallery to the studio floor, or whatever, or whether it's being multiplexed onto a CWDM multiplex and sent with many other signals between buildings. I've done a lot of work at Arsenal, and they have video routers at 3 locations: in their studio in the stadium, at the OB Park in the stadium, and at Highbury House, which is a mile down the road where their post-production facility is. And their 3 routers are all connected together over a little fiber ring, and they've got the optical SFPs in the back of the routers, so there's not even any outboard conversion equipment. The CWDM SFPs sit in the routers, and then it's just they hit a multiplexer, and that feeds a ring that goes between all 3 facilities. So that's a very cute sort of way that they solved that problem. With all that kind of history and all those variations and all those kind of ways that SDi is used, we have to think about what it is we're doing here from a physics point of view, from an electrical point of view. And so we've got we saw earlier with that silly big Victorian picture, we've got coaxial cable, which is a center conductive core, a dielectric material around the core, and then in the case of SDi, this stuff, a braid that goes round the dielectric, and then a jacket that goes on top of that. And the reason we use coaxial cable is for bandwidth purposes. The 2 different kinds of cable we deal with as engineers are twisted pair copper, for audio, for data, and that kind of thing. And the reason we use twisted pair is because we can exploit common mode rejection. But noise is not the big issue with digital video. The big issue with digital video is bandwidth, and so that's why we use coaxial cable. And you can think of a coaxial cable as being a long length of many resistors in series with capacitors and associated resistances across them between the screen and the core. And so this obviously put out of your heads thinking about DC, about just volts, but think about megahertz and gigahertz. What does that cable look like to the transmitting piece of equipment? Well, it looks like a long line of resistors and capacitors. And if we construct this cable just correctly, we can give that dielectric material the right characteristic to make this cable look like it has a nominal impedance all the way down it. And the standard that we adopted, many years ago in video is 75 ohms. And so, I mean, it's ridiculous. If I take a voltmeter and I measure across this cable between the screen and the pin at DC, there's no conduction at all. Tens of megohms of resistance. But to those very high frequency signals, it looks like a continuous impedance of 75 ohms between the pin and the screen. And if we can keep that consistent down the length of the cable, we can then drive the cable appropriately so that the signal will go the furthest possible distance. And at the far end, we want the terminating resistance of the BNC at the receiving piece of equipment, in the back of the monitor, on the back of the vision mixer or whatever. We want that to look like a 75 ohm impedance to match the cable. And the sending piece of equipment, the little launch amplifier in the back of the camera CCU or in the distribution amplifier or whatever, we want that to drive the line with a sending impedance of 75 ohms. And so 75 ohms into this cable, which has a nominal impedance of 75 ohms all the way down its length, and a receiving impedance of 75 ohms at the other end, gives us a balanced signal that if we arrange the driving amplifier correctly, we can get the most out of the cable. And so think about the cable. It's a series of capacitances with shunt resistors across them, and kind of, you know, that's the thing that allows us to calculate the impedance. And so we want to be in a position where we can say all those physical considerations. So the inductance per unit length, which is L, the inductance per unit length, which is L, the conductance per unit length, the dielectric, this is all getting a bit physicsy, and the capacitance per unit length, all are relatable in this way, so that we can build a cable that behaves like we want a well-behaved video cable to behave, 75 ohms nominal impedance. And one of the things that's worth considering, so I mean, here's a piece of standard, or what we call standard definition video cable. It rolls off the tongue very easily. I mean, this will carry 12G if you want it to, not very far, but it'll carry 12G. But this piece of cable here is what's sometimes referred to as SDO1, or Image 360, or Belden 1855 if you've bought it from Mr. Belden, and it's kind of skinny coax, which is probably the source of some of your problems. You know, this was great for standard definition video. Okay for 1.5 gigabit video, starting to show its age a little bit with 3 gigs. And when we get to my test results that you know, go over this whole process of testing all these different samples of cable, you'll see just how this performs next to its kind of thicker cousin. So that's, as I say, Image 360. That's probably what you guys refer to this as. And interestingly, the 360 actually means 360 megahertz, which is an analog measurement. And 360 megahertz, it means that under the specified length of 100 meters, 360 megahertz signal will not have lost more than 6 dBs of amplitude if this cable's been terminated correctly. That's what the 360 refers to. This cable here, which is this is Belden 1694A, which is you know, pretty ubiquitous for you know, new installations nowadays. Also referred to as SD13 if you ever bought it from Bryant Broadcast. It's not the same as Image 1000. Image 1000 is a slightly lower specification cable that Argosy now own the rights to, but it's built in a slightly different way to this. If you were going to give this like an image certification, you could call it Image 4.5 gigahertz, because this cable supposedly at 50 meters gives you better than 6 dBs worth of amplitude loss at 4.5 gigahertz of analog bandwidth. And so you can see that Image 1000 actually is only 1 gigahertz, 1000 megahertz for the same specification. And when we go and look at the test results, you'll see that Image 1000 fares worse than this stuff. And the reason, I've chatted, so this, in Europe, this cable used to be manufactured by a company called Conductfil in Spain. And I've been out for dinner with the guys from Conductfil at IBC before, because kind of it's all about the cabling. That's what used to get me excited at IBC. But they used to say that the difference between Belden and every other manufacturer of high performance video cable is that Belden have this patented process for the dielectric, whereas every other manufacturer, when the cable extruding machine extrudes the center core and coats it in that foamy dielectric. I mean, no doubt you guys have chopped this apart and used your snips to, you know, sort of like nibble away at the center dielectric. If you haven't, give it a go. It's interesting. But the central dielectric on this cable that comes from Belden is they use a process called nitrogen inflation, where as the cable's being extruded from the machine with the center core and the braids being put on, and then the PVC, it's not PVC nowadays, but the low smoke zero halogen jackets being added on, they force nitrogen down the center of the cable while the dielectric's still soft. And apparently that inflates the dielectric a lot better and gives a much more consistent dielectric performance. And so G in this equation here, the conductance per unit length is much more consistent if you use nitrogen inflation, whereas Image 1000, they use a mechanical inflation. Essentially, as they put the braid on, the braid pulls the dielectric material into position. And so that's why Belden cable is considered much more superior for these high data rate video signals. Now, Belden do another grade of cable called Belden 7733, which is a lot thicker than this, and it's like a hose pipe. you know, and it's a bit better, but it's not, you know, it's like 3 times the price and twice as hard to work with, and your wireman has to buy a new crimp tool and all that kind of stuff. So in my estimation, if you're having to rely on the tiny little benefit that Belden 7733 brings to the party, you're flying too close to the hairy edge. And there will be other things, like the difference between, you know, video equipment that will bite you in the arse if you're flying that close to the wind, kind of thing. So for my money, this is the last word in copper from an economy and from a performance point of view. Belden 1694. So
you mentioned the Image 360, which is what the vast majority of our CTA is wired in, because it's small and it's compact. Well, it's not small, but it's distances are short. An Image 1000 is really only used between the two CTAs.
Yeah.
So if we're doing, and the route that our cables take and the patch fields that get introduced, you know, we could be seeing 30, possibly 40 meters of Image 360 with some patch bays and turn panels around it.
Yeah, I mean, people forget.
We're getting concerned.
People forget that you know, once a cable gets into a bay, it's still got 3 meters to get up the bay and have a nice swan neck onto the panel or onto the back of the router or whatever. And so you can very quickly in an MCR chew up lots of length. But consider this: consider that you've got you know, signal coming out the back of a router, and it goes, you know, has to come out the bay. Maybe has to travel 10 bays down the MCR to the turn panel that then feeds off to somewhere else. The fact that it's going on high quality cable from the turn panel onwards doesn't negate the fact that damage has been done in that skinny coax between the back of the router and the turn panel. Now, if the last thing it hit before it left the MCR was a DA, then okay, you're good. You know, the signal's been given the brush and wash up, and it's now much better. But mixing a run, you know, from the back of a router or the back of a vision mixer or whatever to a CTP, then out on good quality cable to wherever it's going, you know, just means that, you know, it's been given a bad start in life, kind of thing. So let's wait till we get to our, you know, all our cable test results, and you'll be able to kind of see what those effects are. This slide here is nicked from that Tektronix application notes PDF that's in that folder I sent out in the chat earlier, and this shows us what we have to think about. So this is the legendary I pattern, and you know, if I go back to stop sharing that, if I go back to my leader and I take my I pattern full screen, that's a live I pattern of the 3G signal that I'm feeding from a test signal generator at the moment, but I mean, this is obviously makes it a lot clearer. You can see that we've got a bunch of kind of crossovers. You know, so the signal starts low, goes high, you know, for a certain amount of time, a unit interval, UI. Remember that abbreviation. That's important, and then drops down again. And so what the I pattern is it's taking the digital bit stream, the ones and the zeros, and overlaying it on itself many times, so you get a feel for the quantity, for the quality of the 0 to 1 and the 1 to 0 transitions of our signal, because that's all that really matters, isn't it? Whether those ones and zeros, whether that binary data is getting through successfully. Now, if you did you know, IT or computer science at school or university, you'll be used to looking in books and seeing digital waveforms that look perfectly square. You know, it rises from 0 to 1 in an instant and stays at 1 and then drops to 0 again in an instant. That's not the case. As we said before, every signal that's being pushed down a cable is analog. You know, you might think of it as digital, but actually cables are analog, and you know, the volts that are carrying that signal you know, are analog volts, and they suffer all the degradations of analog electronics. And so, you know, with distance, you know, attenuation sets in, and the voltage gets lower, and you know, with mismatches down that cable, where we haven't got quite consistent dielectric conductance and impedance figures all the way down that cable, we get what's called jitter. And so in the Y direction, in the sort of signal level direction, which starts off at 0.8 of a volt as it leaves the piece of equipment, over the distance of the cable, that will drop off, and by the time it gets to the other end, will be lower than 0.8 of a volt for sure. But also, we suffer what's called jitter, whereby the ones and the zeros don't align perfectly on top of each other. The timing characteristic of that cable is not consistent all the way down. And so those tiny misterminations where the dielectric isn't quite perfect, we get small reflections and small imperfections in the impedance. And so we get what looks like a smearing in the time direction. The signal isn't perfectly aligned, and so we get jitter. Added to that, distance and attenuation causes what's called rise time errors. That the signal isn't able to rise from 0 to 1 instantly, and it's not able to drop from 1 to 0 instantly because it's a limited bandwidth system. We get what's called overshoots and undershoots, and so we have things to consider. We have the rise time to consider. We have how much jitter has been imposed on the signal and how much amplitude we've lost to the signal. These are all the things that basically tell us the health of our digital video signal as it goes from the back of a piece of equipment, vision mixer or whatever, to the receiving piece of equipment, monitor or input to an EVS or whatever. And so as these effects get worse and worse, our eye pattern closes and it gets more and more smeary. So what you can see on my leader is just a couple of meters of this stuff, this Belden 1694. And so that's about as good as SDi gets. That really is. In real world terms, that's as good as SDi gets. And that's fine. Equipment can recover those ones and zeros very easily. The clock edges are very obvious, and that's fine. But before we go over all my test results from when I first did all the 3G testing, I've got, switch back to my camera. I've got behind me 60 meters of various lengths of Belden, and I'll just increase that length through the scope. I'll keep plugging on different lengths, and you can see really what happens as we go to longer and longer lengths. The amplitude gets lower, and the jitter gets worse, and the rise time degrades, and you'll be surprised just how bad the eye pattern gets and how many errors the scope's logging before you start seeing splats and drop frames and problems with the signal. So generally speaking, the receiving amplifiers and equipment are so good nowadays; they cover a multitude of sins. And this is the problem. This is the problem that we're in a situation whereby the equipment is not alerting us, to when things are on the hairy edge, and it's why. If it's a problem for you guys, you'll get very familiar with the physical layer measurement facilities on your scope, whether it's a Tektronix 8000 or a Leader 54 series. If you're worried about 3G, don't expect the equipment to reveal this to you. And it's kind of the same as Ethernet, really. With Ethernet, you can push it very, very far before you start noticing disconnects. Ethernet's if you're running TCP over Ethernet, TCP will cover a multitude of sins, packet retransmissions and all that kind of stuff will cover the fact that your cable is losing half the packets that are being sent down it. Similarly with 3G, the receiving equipment's very good at making the best of a bad job, but you don't want that. You want to know when things are kind of falling apart.
You mentioned you mentioned about receivers and things, and we are noticing, I don't know whether you have much experience with this, we're noticing that at HD and 3G, some of our receivers not to be as good as others, i.e., a Fabrics resolves most things, whereas a Blackmagic box doesn't. I assume that's down to, you talk about 75 ohms termination. I imagine that's what they're both using, but we're noticing massive differences in I say what we get on the end of a bit of a test equipment as we do to some apparatus.
Yeah, no, you're absolutely right. And it is all three things to consider. It's the sending piece of equipment, how well it drives the line. It's the receiving piece of equipment, how well it terminates the line. And if it does that poorly, that gives rise to a phenomenon called return loss. And it's the quality of the transmission line. I mean, this is no different from any other kind of transmission system you might be able to think of, Ethernet or anything else. You have to drive the line correctly, the line has to be good, and the receiving piece of equipment has to behave well. Now, the thing you notice with Blackmagic is that they quite like their PCB mounted BNCs with the right angled center on them. It's very hard to get good return loss if you've got a right angled pin on the BNC. And so the very best quality equipment, the BNC tends to mount in a cutout in the middle of the PCB. It sits centrally within the PCB, because then the pin can go straight onto the board, and very soon behind the pin, you've got the receiving amplifier. Whereas the Blackmagic, I mean, they're blinking built in the same factories that build graphics cards, aren't they? They're built to a price. They're built to domestic standards. And they use those BNCs with the right angle pin, and so that's quite often the problem with Blackmagic gear. It has a terrible return loss. I don't know if I was just talking to Michael or whether you all heard this, but at 3 gigabits per second, the SMPTE spec is that return loss should be better than 18 dBs. And the EBU has a slightly, well, we have to go and look at the document. What SMPTE and the EBU have got, one's slightly more generous than the other, but 18 dBs of return loss is considered, the limit for 3G SDi. There are some bits of Blackmagic gear I've measured, particularly the little video routers, where they've got worse than 12 dBs of return loss on those input BNCs. And so, whereas something landing on the back of a proper piece of video equipment, a Sony VTR, a Tektronix scope, a Probell router, something from the old school, would have no trouble driving the line, because the return loss coming back out the BNC isn't an issue. When it hits the back of a piece of Blackmagic equipment, and twice the signal that's actually allowed is being reflected back up the cable, flipping, interfering with the incoming signal, which is what we call return loss. You suddenly find that, you swapped out an old school Probell router for a new Blackmagic router, and all of a sudden, none of those input feeds are working correctly, and you're scratching your head. Is it the cable? Is it the senders or whatever? No, it's the return loss on that piece of equipment. And so that kind of sharpens the mind for maybe moving to fiber optic sooner than perhaps you would have to. This is a screen grab from a Tektronix 2300 with the physical layer option, and this kind of again shows a very good, very short length signal with only a tiny amount of loss from the 800 millivolts that would have been sent down the cable. Really good rise and fall times, 80 picoseconds. That's 80 times 10 to the minus 12 seconds. That's not very long, is it? And so that's a really very, very good. Never gets any better than that kind of SDi eye pattern. So I don't know. It's probably down to how many thousands of bits are allocated to the receive buffer or something, but it's many bits being successively overlaid on top of each other and presented for your sort of entertainment. So when you look at this on my leader scope here, and if I go to the options, I can go and look at many more eye patterns. And there's 16 UIs, unit intervals, which is obviously a different amount of time depending on whether it's 1.5G or 3G or 270 megabits or 12G or whatever. People tend to use either 2 UIs or 4 UIs. It's easy to look at. There's kind of 4-bit transitions that we can look at, but we have no idea where they came from in the bit stream. But it's just to give us a feeling of the health of the bit stream. It doesn't really matter whether they're taken from a pixel top left of the image or whether they've come from the metadata between frames. It's just the bit stream being overlaid upon itself many times. So we're seeing an up-down transition there and a down-up transition there. And the fact that we're seeing as many up-down transitions as down-up transitions is just because, for a large number of bit transitions in an SDi stream, there'll be the same number of 1s to 0s as 0s to 1s. And that's what we're worried about. We're worried about the health of the physical layer. What is this cable doing to the bits that are coming down it? Because those bits, although we call them bits, although we think about them as digital 1s and 0s, they're actually just analog transitions coming down the cable. So when you're talking about physical layer considerations, the eye pattern is the only thing that really matters. The eye pattern is really showing you what's coming down the cable. Of course, once you've successfully received the signal and you've turned it back into digital video bits and turned those into pixels, we are a couple of layers abstracted from what went on the cable. But for today's purposes, we're only worried about what's coming down the cable. We don't care if this is serial digital video or whether it's an ASI signal between the back of a transmission encoder and the multiplexer that's sending it off to the satellite facility or whatever. We're just worried about the quality of the signal that's coming down the cable. Now, we're still back in the 1.5 G, 1.5 gigabits, so 422, 50i, standard sort of television stuff. So here's 100 meters of Belden 1694. So literally all I did was I took a 100-meter drum off the shelf, put a BNC on each end of it, stuck it on the back of my Tektronix, and I looked what I got. Tektronix has a very nice SDi status display that gives you a little sort of what would you call that? Like a bar graph of green is good, yellow is inside spec but starting to worry, and red is outside spec. And so if you look at the left-hand slide there, you can see that the bar graph hasn't even started to register any problems at all. And again, there's our very, very good eye pattern, superb. We can see all the 1s to 0 transitions and everything. 100 meters of good quality, probably not the very best, but the most affordable good quality coax, Belden 1694A, and that's what we've got. And so the Tektronix is kicking off big time about jitter and about the attenuation on the signal. But look at the eye pattern. It's like it's a bowl of porridge, isn't it? You can't even see any transitions there. But amazingly, the scope is able to recover that picture and reconstruct the image, and you can see the waveform there. Now, what you don't see is that every few seconds you've got banging and crashing and pixels going funny colors and frames being dropped and such. But it is just testament to how good the receiving electronics in good quality broadcast kit is, that it can take that eye pattern there, which just looks like noise, and can actually recover a video signal from it in any kind of way, shape, or form. That kind of just blows me away, really. Now, we've talked about return loss. Return loss is the ability of a piece of equipment to receive a signal cleanly without pushing anything back up the line that's going to impede the driving of the signal to the end. The worst case I saw of this was in the Orange Tower in Media City, near where you guys are. So when we built that facility in 2013 or whenever it was, we took the view that one side of the building, all the runs to the edit suites, the grading rooms, and the audio suites, and everything else was reliably under what we decided we'd keep our 3G performance to. But the other side of the building, being a much further initial run, they were all either at the limit or further than the limit of what we felt comfortable with. So we put fiber in one side of the building. So all the edit suites on one side of the building were over fiber, all down the other side were over copper. Now, of course, at each position, we had to have a fiber receiver to turn it back into copper to drive the piece of equipment. And there were several slung TVs in a common area, for them to be able to show, whatever, the play out of Coronation Street or whatever. And we found with one that with my trusty Tektronix scope, the output of the fiber receiver looked fantastic. As soon as I plugged it into the HDMI converter on the back of the TV, no signal at all. And what I realized was that the return loss on the cheap and cheerful SDi to HDMI converter was so bad that the little sort of half-meter cable on the back of the TV, so you can imagine the back of the TV had a fiber receiver and an HDMI converter velcroed to the back of the TV, and just an SDi loop between the two. the return loss on the HDMI converter was so bad that it was completely swamping the output of the optical receiver. So we replaced it with a cable that was 1.5 meters long, and Wyman did a nice little loop, and it worked perfectly. So return loss not only bedevils you for long runs, it can kill the ability of a piece of equipment to receive the signal on long runs, but it can bedevil you on short runs as well, because there's not enough length of cable for those reflections to be absorbed over, and so return loss, and it's always cheap equipment that has poor return loss. But what that tells you is that what worked well when you installed the facility with all your Sony and Tektronix equipment may not be so good once it's all being replaced with AJA and Blackmagic equipment. So here's that formalized testing of 3G that I did back in 2009. And the full PDF of all these screen grabs is in that folder that I sent in the chat earlier. So you can look at that if you want to. And the columns going across the top there are the different cable types. So we've got Belden 1694. Then we've got the no branded conduct fill equivalent. And remember, conduct fill were Belden's manufacturer in Europe. And so if you bought high definition video cable from Bryant Broadcast for the last 10 years, Bryant are out of business now, unfortunately, but they were carrying conduct fills, no branded cable, and they used to call it SD13. But it came off the same production line as Belden. It was the same cable, and it was like 30p a meter cheaper. And then you've got Dracker DVC 13C, which is also known as Image 1000. That's what people call that. So that those first three columns there are thick video coax, and then the next three columns are what you call skinny video coax. So you've got the Belden 1855, which is this, and then you've got the conduct fill equivalent of that. Again, Bryant were sort of funding this exercise, and so they wanted to see whether conduct fill really were providing them with a cable that performs the same as the Belden. And then you've got the Dracker, which is also referred to as Image 360. And then we've got lengths. And so obviously we started this process at very long lengths and chopped the cable down, re-terminating as we went. And so, it wasn't as if we cut a meter and then cut 2 meters and whatever. So we started with very long cables and went down to very short cables. But you can see, it's quite a nice image in the multi-view on the Tektronix. You can see the eye pattern, and bottom right on each of these little mini pictures is the what I'm trying to say is the video. And so you might recognize that as being a pathological test signal. So a pathological test signal essentially is designed to provide long runs of ones and zeros, just to make sure your SDi clockers and reclockers at the other end are doing the right thing and recovering the clock signal, all that kind of stuff. So we start off at a meter length, and everything on all the cable types, the fat, thick coax and the skinny coax, looks great. And as we go down longer and longer distances, you can see the eye pattern gets worse and worse, more degraded. We say the eye's closing. So, if that's a nice wide open eye, down here, that's a very sort of droopy closed eye. And you can see exactly what the effect is. Rise time is being degraded. Rise time's quite good there. Rise time is being degraded, and attenuation is setting in. The signal's getting less and less. It's no longer 800 millivolts. It's now 700, 600, 400 millivolts, and also the jitter, that sharp distinction between the rise time of a 0 to 1 transition and that sharp distinction between the fall time of a 1 to 0 transition is getting worse. So by the time we get to sort of 40 and 50 meters, you can see the eye pattern is very poor. And if you look closely again, you can download the what am I trying to say? The PDF with all of this on in full res to see a bit better. It's clearly down-resed it for these slides. You can see how much worse that's getting. And as we go along in the X direction between the thick coaxes and the skinny coaxes, we can see the skinny coaxes are suffering a lot worse. I mean, amazingly, the signal's still being recovered. Look at that. Even though we've got kind of maximum errors on the Tektronix and the eye pattern looks like just noise, the equipment's able to recover it. In fact, here's the same stuff continued. And in fact, we got all the way up to 160 meters. And, you know, look, I mean, is that just a green line or is that an eye pattern? Who knows? But again, the Tektronix, at least with the fat coaxes, is recovering the picture. And somewhere between 160 and 170 meters of these high quality sort of thick coaxes, the Tektronix even loses the ability to recover the picture. Now, again, what you wouldn't have been able to see on this static image is the fact that each one of those was banging and crashing, and you're seeing green and purple splats the whole time. And in fact, obviously that little screen grab there, you know, that's, you know, it's just managed to grab a few pixels of video data before it fell over. And so, you know, that's essentially what we're dealing with. We're dealing with different cable types and different lengths, and that's the effect that we have. And the eye pattern tells you everything you need to know. You know, you don't really have to worry about, you know, attenuation and rise time and fall time and jitter. Maybe you do in some very specialist circumstances, but for the most part, a quick glance at the eye pattern, that's acceptable. At 50 and 60 meters, that's getting to the point where it isn't acceptable. You know, that's kind of our limit. So here are some of my conclusions from those tests. At 3G, using coax specified, 60 meters is the workable cable length before attenuation below 400 millivolts becomes an issue. And you know, 60 meters is always the limit. If people approach me about installations, I say if the cable run is more than 60 meters, and in truth, that's really 50 meters, because once it's got in and out of the bay at each end or whatever, you know, that's where I say no, we really have to do this in fiber. SD coax goes about half the distance, and that seems counterintuitive, because SD coax was built for 360 megahertz of analog bandwidth, whereas you know, we're dealing with much higher analog bandwidth supposedly on these cables. That's just reflective of the fact that the equipment's got a lot better at receiving the signal since SD days of the 1990s. The variation between the most expensive cable, Belden 1694, and an Image 1000, if we're thinking about just HD style cables, is not great. And it gives you about 10 meters more of distance. And if you're relying on that, well, you're sailing too close to the wind anyway. You know, it would be the same nowadays as saying we're going to wire everything in Belden 7733 because that gives us an extra couple of meters at 12G. No. If you're sailing that close to the wind, you really should be thinking about fiber. And the conduct fill 1694 equivalent tracks the more expensive Belden cable very well. In just a minute, I've got the same measurements through U-links, patch panels, you know, barrels, that kind of thing. It turns out that those things don't have they don't add much difference. A little bit, not much. Cable really is the thing that kills you. Yes, so let's zoom in on this guy. Remember, the last three columns are image are skinny coax, so what you call Image 360, Belden 1694, the conduct fill equivalent, and the Dracker equivalent. We start seeing red warnings from the Tektronix down at 40 meters. But at 30 meters, we've got, you know, yellow warnings. It's starting to get close. We're having to do error correction. Whereas when you get to the red dots, the Tektronix was having to do error recovery. It was having to fill in the blanks. So somewhere between 30 and 40 meters, point to point, with skinny coax, Image 360, SD01, Belden 1855, whatever you want to call it, you're starting to hit the limits of the specification. Now, that's not to say you're not recovering pictures, but you're recovering pictures with some caveats. Yes, if you remember channel conditions on VTRs, you know, green channel condition, all good. Amber channel condition, the VTR was having to do some error correction. Red channel condition, the VTR was having to do some error concealment. So in essence, you never want to be out of the green zone, do you? You know, you want to be safely, you know, with a little bit of headroom. You want to feel like, you know, somebody could tread on that cable and it's not suddenly going to make the pictures fall apart, or you know, you have a very hot day, you know, and everything warms up a tiny bit, and you know what I mean. You don't want to be sailing too close to the wind. So, but you know, peruse that big PDF. I think it's called Tektronix Plots or something that's in that folder at your leisure, and you'll get a feel for where all those figures take us to. So there's conclusions. This is a screen grab from my leader. It'll be exactly the same thing as when you press the config button on a tech and you go to the PHY menu setting, physical layer setting. You know, you can specify what things we're checking for and rise times, fall times, etc. And again, if you look in that folder, you'll see the EBU tech report for 3G, paper copy there, and that tells you all the things you need to be looking at SMPTE 259, SMPTE 292, SMPTE 424, which is 3G. You know, what you need to be seeing on your Tektronix to know that you're within specification. And example of what just 2 meters of that good quality Belden 1694 cable looks like at 1.5G and 12G. So 12G is even more of a challenge. And in fact, I won't go over it now because it's not a concern for you guys, but here are all exactly the same figures for 12G cable. And, you know, if that's the limit there, if that's the limit there, 600 millivolts attenuation, that's where things start getting hairy. You can see that our distances for 12G are between 10 and 15 meters, depending on which cable type you go for. And that's kind of not really usable, is it? I mean, it's all right for bay to bay, but you know, you're not going to run to an edit suite or to a studio gallery over 12G. And there's no surprise there, because 12G is 2 octaves higher than 3G. And 2 octaves of additional bandwidth. It's just a bandwidth distance product. So say 15 meters best case for 12G, you know, double that and double that to accommodate the fact we've gone from 12 to 6 to 3G. We're at 60 meters, which is exactly what we found with the 3G testing. So no surprise there. 12G is a real challenge to the industry. And in fact, I also tested it with the various super expensive gold-plated BNCs. They don't make a blind bit of difference. Between a tiny difference in almost immeasurable difference, depending on the cable type, between you know, the fancy gold-plated, you know, £5.95 BNCs and just the regular 3G, you know, 98 pence BNCs. So don't be fooled by gold-plated stuff. It's the same with blinking audiophiles, isn't it? Hi-fi nuts, you know, they like gold-plated stuff. But that's essentially, you know, the little presentation on 3G and physical layer considerations and all that kind of stuff. My next point was going to be to just do a bit of a practical demo and put the leader full screen and just splice in longer and longer cable, so that you could see in real time, you know, the eye pattern degrading, you know, to show you that I'm not kind of making this all up. It really is like that. So you should be able to see a browser window that I'm sharing. This is that folder I've been pumping out in the chat. You know, you may find these documents useful. There are the notes from that first session. That's an error log captured out of my leader. It's remarkably similar in format to the error log you can extract from your Tektronix. You know, so it's really good. You know, basically, it logs things against time code, and you can see where, you know, if you've got a real sort of hairy edge situation, you want to see where all of a sudden a link fell over. That's a very good way of doing it. Just leave it logging, and then go and grab the log afterwards. EBU tech report, which I'm going to talk about in a minute. That's this bit of paper, which is basically all you need to know about the specifications for 3G. So you don't really need to know them, because you know, with your Tektronix, that already comes preset on the physical layer button. So when you call up a physical layer measurement quadrant and then bring it full screen, and you hold down the quadrant that you've got full screen, and you set the options for that quadrant. So long as you've selected for 3G, all these you know, sort of standards that are written down in here, they get preloaded to start doing analysis on your tech. So this is very useful and interesting, this document, the EBU report, but not entirely necessary. And then those JPEGs are all screen grabs from the leader that's behind me. This one is just a is just a screen grab of a couple of meters of image 360. All the others are screen grabs of varying lengths of Belden 1694. In fact, they're the lengths of Belden 1694 I'm about to start fiddling around with now. Then there's a Tektronix document called jitter measurements, which again is useful, like the EBU report document. This is one I often refer to. Particularly useful nowadays as people are getting their incoming lines coming over IP. And when it gets turned back into SDi, they discover that the jitter that's been imposed on the signal by the IP encode, decode, sent through somebody's cloud, somebody's virtual environment, is now made the SDi too jittery to be usable. And then this very last one here, techplots_path, short for pathological, is that entire document of all the Tektronix results of the varying 3G cable types. So I'm just going to open that up on screen. Barrels and U-links and things like that. You'll see that down at the bottom of that diagram, which wasn't obvious from the little snip I did in the main presentation, you can see what manky old flipping U-links and brand new style of U-links and compact high density U-links and BNC barrels do to the signal, comparatively speaking. And they're all with 10 meters on one side of whatever we're putting in the way and 10 meters on the other side. So you can refer back to the 10 meter chart and see how it's affected it. But suffice it to say, BNC barrels, U-links don't make that much of a difference. They don't make anything like the kind of difference that another 10 meters of cable makes, and they don't make anything like the difference that you get in variation between equipment. So, if you're thinking to yourself, oh yeah, we can squeeze a bit more life out of this link just by using a gold-plated U-link, you're looking in the wrong place for benefits there. It really is cable and the quality of cable that kills your signal. And there's also, just at the end of that, at the end of the presentation, there are some extra additional reading, things that I found really useful. There's the EBU report. I write a blog reasonably regularly, and you can kind of find a lot of stuff that I've discovered or things I've come across on there. That's another Tektronix SDi jitter measurement document, a slightly different one, written by somebody in Tektronix Japan. Same sort of stuff, but I found it a bit easier to read, not as dense. The art of digital video, John Watkinson, that's the definitive text. Should be copy in every workshop. And digital signal processing, which is more general digital transmission stuff. Kenton Williams, which again, they're both very readable and kind of would do you no harm to have a little read of those. So I'm going to put the EBU report up for a second. So again, this is probably from 10 or more, 10 years ago. This is the EBU's advice on how to deal with 3G and all that kind of stuff. And it's quite a good introduction to the standard and the variations of 3G. 3G essentially comes in link A and link B styles. One is level A and level B. One is just the 3G data is mapped entirely, or rather the video data is mapped entirely in a sort of linear fashion onto the 3G link, and the two level B ones are the old dual link standards, but multiplexed onto a 3G link. Most equipment supports both styles, but just be aware that you've got two different styles of 3G, level A and level B. I've never known a piece of equipment not support both, but maybe there is, I don't know. Some advice about testing and how AES is embedded and all that kind of stuff. But section 5 is the real meat of the thing, and it's again might be useful for you. That's where I stole that great image of the eye diagram, and there are the various standards for SD for 270 megabits, for 1.5 gigabits, and for 3 gigabits. And the slight differences there exist between the ITU, the International Telecommunications Union, and SMPTE, those jolly old Americans. The slight differences that between their standards, but they're very modest differences. Bit of an explanation of return loss and jitter, and how much jitter is acceptable, and the thing that you have to remember when measuring jitter, which if we go back to the eye diagram, is the is the loss of sharpness of rising and falling edges. You know, where those bits are starting to move around. You know, in the time domain, is that we have to decide over what time sort of period we're going to make that measurement. And so typically people will say it's measured over 100 kilohertz or over 10 kilohertz. And that basically tells us whether we're worried about those much longer jittery effects, like so the jitter you get with bad IP encoders is sometimes referred to as SDi wander, and it's SDi timing variation that happens, you know, over 10 hertz, you know, just a few cycles per second. Whereas the kind of things you'll start seeing appearing on your cables, you know, if you're having to drop down to 10 kilohertz filtering on the iPad to see it, then you've lost the battle already. So we pretty much always measure all jitter at with 100 kilohertz filter, which means that we're seeing those. I mean, because these are flipping 3 gigabit per second transitions. You know, 3,000 million transitions per second. You know, there's no point, unless you're worried about sort of very gross effects, looking down at those low frequency things. So you'll typically, the default will be, you'll set your test instrument to 100 kilohertz as our measurement style. Look there, there's wander, or sometimes called SDi drift, and that's, you know, sub 10 hertz type changes. But again, lots of the standards there. But you know, it's kind of interesting, and you might only ever look at this once to confirm that your Tektronix is set up correctly. But the preset inside Tech and inside the leader as well is correct for sure. And here's some you know, some guidance on this is more for sort of manufacturers and sort of like cable equalization and how you build a good cable equalizer, and you know, what you can expect, you know, how the analog performance of cables drops off over distance with attenuation. So yeah, that's a jolly good document to have to hand. The EBU advice on the use of 3G technical report number 2. So there you can see the leader with, as we said before, the 2K, so slightly higher res than the kind of video that you guys deal with, and 50p. So definitely a 3G signal, and the leader tells us that it's 3G level B dual link, and you know, we can obviously, you know, call up different test settings or whatever. But at the moment, all we're seeing is, I'm just going to stand up. Thankfully, got a microphone on my head. So at the moment, there's just a little short length of cable at the back of the leader. And so, yeah, that digital signal is as good as it gets. So I'm now going to grab 10 meters of this Belden coax, and then you can see at the bottom there the various measurements. TR and TF is transition rising and transition falling, and then we've got the total jitter and so TJ and CJ. I'm going to have to go back and look at the document. They're 2 jitter measurements, one of which is, yeah, I'm going to have to go back and look at the document. But in a sense, it doesn't really matter, because the leader will start flagging these up when they get close to the hairy edge. You'll notice as well as these things being sort of displayed in picosecond measurements, they're also shown in those interval units, IUs, which kind of frees you from having to think about, oh, what standard am I working at? Am I working at 3G, or am I working at 1.5G or whatever? So there we go. You can see that our 2 jitter measurements have risen a little bit. And if I go into the eye measurement page, I set up, look, there you can see where we can select a filter, and the default is 100 kilohertz. So upper menu and error setup, and we are on the 3G page, and you can see, is that clear to you guys? Can you see the can you see I've got all those tests turned on? So rise time error, fall time error, delta error, which is an average of the rise and the fall time. That's kind of reflective of both of them, I suppose. Current jitter error and timing jitter error, and there's the specification there. 2 UIs and 0.3 of a UI, and the leader very helpfully gives you those measurements in picoseconds as well. So I mean, these are flipping tiny little measurements. If you think that, you know, an HD pixel is 12 nanoseconds, you know, and there are 1,000 picoseconds in a nanosecond, we're right down in the weeds here. You know, so 1,000 picoseconds is a nanosecond, 1,000 nanoseconds is a microsecond. You know, a line of video in HD terms is, what is it? Help me out, somebody. It's 24 microseconds. Do you know what I mean? Well, we're right down in very tiny time measurements here. So amazing that yeah, a piece of equipment that you know, you can own in your TV facility can make such fine and such precise measurements. So there we go. So there's our eye pattern, with having added 10 meters of cable from the test output back to the input. Now, first observations are, I suppose, that our level is still pretty good. You know, we haven't got much attenuation yet. You know, we're nearly at 0.8 of a volt on the level of the signal, and you know, we haven't got any sort of red conditions yet to warn us, or no yellow conditions to warn us that we're getting close to a hairy edge or anything. So let's go a bit further, and I'll take another 10-meter length of coax, and I'll connect that in. Now, you might be thinking to yourself, every time he connects an extra length of coax in, he's sticking in a couple of BNC barrels, which I am. But in a sense, you know, this is kind of reflective of what people in facilities have to do. You know, when you know, they have to put things through panels, they have to put things through CTPs or whatever. So if I take that off there, right. So now let the thing settle down. Now we've got 20 meters of Belden 1694 in the way, and so our amplitude has dropped off a little bit now. We were at 690 before, we're now at 640, so we lost a bit of amplitude. And to be honest, amplitude is normally the thing that's the best indicator of when things are going to fall apart. But look at the eye pattern. You can see that the eye pattern is considerably more mushy than it was before, and the rise time the rise and fall time are terrible by comparison. This is not the nice square wave we wanted to see. So if I now take another length of coax, so now we've got 30 meters of coax in the way, and we're already seeing an error. So I suspect that's a rise and a fall time error, because we're not getting a rise and fall time measurement anymore. But our amplitude's still okay, and you know, our rise time, our timing jitter figures are still okay. So we're still kind of quite comfortable. You know, 30 meters. I mean, this cable's kind of all coiled up, and it's been in and out of boxes, and I don't know how good these BNC barrels are, but at 30 meters, we're starting to see an error being flagged up. So let's you know, continue. Let's put another 10 meters of cable in the way. And again, where amplitude is even further down, jitter's still okay, but I mean, look at the state of that eye pattern. That's not very clever, and we're getting errors. So you know, if we were to go and look at the error log on the leader, we can see you know, it's starting to, you know, every time there's a no signal, that's when I was fiddling around with disconnecting and reconnecting cables. But you can see that we're starting to get eye pattern errors coming in there. So that's kind of useful that the machine is kind of following us and logging these things. But yeah, look, that's so let's go back to the multi picture. And you know, it's recovering the signal just fine. You know, even though we're getting SDi eye pattern errors, you know, it's not dropping any frames, and we're not seeing any splats on any pixels yet. That's still kind of okay. But let's continue and put in another 10 meter length of coax, which takes us up to 50 meters. Picture looks okay, but you know, you'd be worried if this was your kind of run, you know, and you know, it's not quite right. But let's put in another length of coax. Right, so 60 meters. This is not good at all. Interestingly, it's still recovering the jitter okay, but the eye pattern is terrible, and the rise time and the fall times are beyond, you know, it's not able to measure them anymore. So even with good quality Bell's End coax, 60 meters is now causing great trouble to our signal. So I mean that really, I suppose, only tells you it's exactly what all those other sort of tests sort of derived. You know, there's sort of no surprises there really. It's exactly as we would have expected. Yeah, I mean, you know, any questions about that side of it?
You were getting errors on the leader, but the picture was okay. So would you say, I'm getting an errors on the leader, I'm going to do something about it? Or would you say, I'm getting an errors on the leader, but the picture's okay, so I'll leave it?
Well, you don't know how close you are to the hairy edge, do you? Modern equipment's very good at recovering things. The leader probably more so than a Blackmagic. I suppose it depends. It depends where your tolerance for getting away with it and being within spec and being certain that if we do have problems, it wasn't because we sort of chanced our arm and expected more out of our cabling than we really should have done. Do you know what I mean?
Yeah, and the error limits within the leader, they're generous or tolerant enough. Are they written for the leader, or are they the EBU spec?
Let's go back to here. I haven't looked actually. So let's go to error setup. So here's the error page for 3G. So 3G error setup, and there's separate pages for HD and for SD. So you can set up. So what have I got here? So for rise time errors, I'm measuring 189. Okay, so actually my rise time errors are set as somewhere between SMPTE 424 and EBU 1120 at 189 picoseconds. So the EBU would tolerate 200. So I could wind that up a bit further for EBU compliance, but it's a bit high for SMPTE compliance. And delta rise time error again. This is set to be as strict as SMPTE requires, but I could wind this up a bit more to 100 picoseconds, and we'd still be compliant with the EBU. In fact, we can't get as high as 100. So these are all the figures here, and you set those in accordance. Well, they should have been set in accordance with the EBU technical report paperwork that's in that folder. So jitter is better than 2 UI for timing jitter and better than 0.3 UI for current jitter. Oh, but interestingly, the EBU one is more strict for those two standards. So it looks like my leader is set halfway between SMPTE and EBU. But again, you know, if you're at the point where you're saying we can pretend we're good because we've picked the slightly more tolerant standard, you know, that's not going to do you any favors in the future, is it? That's not going to. So yeah, when you guys kind of, you know, go back to the MCR now and fire up the physical layer measurement on your Tektronix and start having at it, might be worth just taking this with you. And I bet Tektronix, I bet the default on Tektronix is for SMPTE ST424 rather than ITU 1120, which is more widely used in Europe. But they're just numbers to be measured. You know, rise fall time, or a delta rise fall time, which is an average of the two, and jitter, which is divided into what the leader refers to as timing jitter error and current jitter error. I think timing jitter error is aggregated over a certain number of samples, whereas timing jitter error, current jitter error is measured momentarily at each crossing. And then there's amplitude as well. So amplitude should remain at 800 millivolts, but as you could see, by the time we got to 60 meters, our amplitude had dropped to 520 millivolts. So, but again, these things are to help. You know, they're there to show you where things are going wrong. You know, you might take a view. You might say to yourself, "Oh, those tie lines are on the hairy edge, and they've never given us any trouble because we've got high quality equipment at each end, etc." Or you might find that those runs to that edit suite have always been problematic, and because it's you're driving from a piece of Blackmagic, or you're receiving in a piece of Arduino equipment or something. So, this is I suppose it's hard and fast in some respects because they've actually given you numbers, but in other respects, it's giving you the ability to make some quantifiable judgments, some choices based on the measurements you've taken. And so if you if you're in a position where you have to you can always, again, it works with Tektronix, works with the leader, you can always just export a text-based log with date and time. And in fact, the leader doesn't do this, but Tektronix will do it against time of day time code if you want to do it that way. And you basically, everything in that logging screen that I had up that was checked, that was ticked for making measurements, will be written into the. So this must all be from some stuff I was doing yesterday, because this is all 1920 by 1080 rather than the 2048 by 1080 50p stuff we've got up on screen at the moment. Oh yeah, there we go. This is the logging feature of all these sort of video scopes is very, very useful if you just want to get a feel for how well something's performing.